Thank you all for joining in. My name is Filip Lemic, and together with my colleague Sergi Abadal, I'm going to deliver this invited talk. The talk is entitled Terahertz Nanocommunication and Networking. We're going to talk about emerging applications in the domain. We're going to talk about some approaches for enabling these applications, and we're going to list a few open challenges. So recently we've detected that there are four main or four most promising application domains that can be enabled by terahertz operating nano networks. The first one is software-defined metamaterials and metasurfaces. These are systems for engineered manipulation and control of electromagnetic waves. Then we have wireless robotic materials, and you can think of that as wireless sensor and actuator networks on a nanoscale. Then we had to have a set of applications in the domain of in-body communication, where we have several healthcare-related applications, such as targeted drug delivery, nanosurgeries, neurosurgeries, etc. And then we have on-chip communication, where the main idea is to replace wired connections between cores with their wireless counterparts. So each of these application domains poses a set of requirements on the underlying nano network. And these requirements are very heterogeneous. They're kind of summarized in the table given at the top of the slide. And nonetheless, there are some common denominators in these requirements. For example, the latency of communication should be on the level of the order of milliseconds for software-defined metamaterials, wireless robotic materials, and body-centric communication. The energy consumption in general for all application domains is low or very low. What does this imply? This implies that if you develop a method, an approach for solving a certain problem inside the domain of software-defined metamaterials, this potentially can be extrapolated to other domains that are enabled with terahertz operating nano networks. And this is kind of one of the ideas of this talk, to try to emphasize on the idea of extrapolating the results developed having in mind one application domain to another application domains. So we're going to divide this talk into three kind of topics, three projects that we're currently working on. I'm going to be delivering the talk on Scale ITN, which is a Marie Curie project dealing with terahertz nano networks for enabling in-body applications. And then Sergi is going to take over, and he's going to talk about Visor Circle project dealing with software-defined metamaterials. And he's also going to go through vFlash, another project dealing with on-chip communication. Okay, let's start with Scale ITN. So what are the main problems here that we need to solve? The first problem is attenuation in terahertz frequencies, which per se is very heavy. And then if we are operating inside of a person's body, the range that we can achieve is very limited. Mainly due to technological limitations, the de facto standard communication encoding scheme in nanoscale is time spread on off keying, which is essentially logical once is represented by a short pulse, while logical zero is represented by silences. So having this in mind, the next step is the energy consumption. The energy consumption of the entities in this network of the nanonodes is very low. Very often, if not, well, in most cases, the only feasible powering option is energy harvesting. So they harvest a certain low amounts of energy, and then the nanonodes consume this energy. So at some points in time, the nanonodes can be turned off, and then they harvest more energy until they turn on. So how, in such a setup, the question is, how can you increase the reliability of communication? We want to increase the reliability of communication because we are essentially talking about healthcare, where the reliability of communication should be very high. Usually in traditional wireless networks, you do that with repetitions. So in the graphs given below, we have evaluated what happens on the level of a link in software-defined metamaterials if you utilize repetitions of packets. And what essentially happens that is shown on the graph on the y-axis reliability. You can see that with repetitions, the reliability of a system is always lower than without repetitions. Without repetition is the black line in the graphs, which implies that repetitions here reduce reliability. So this kind of straightforward way in increasing reliability is not possible for energy harvesting nanonodes. So since the energy is so important, it is equally important to accurately model the energy consumption. And currently, well, until very recently, the energy consumption of a nanonode's communication system, assuming TSO-OK, has been modeled by giving a certain energy consumed or certain contributions to the energy consumed to transmission and reception of a pulse. But from more traditional wireless sender networks, we know that the energy is consumed also in idling between transmissions or between receptions of pulses or receptions of packets. So if we contribute a certain energy to idling as well, then what happens, and this is kind of shown in the left-hand side where we model the transmitted energy, the received energy, and the idling energy. What happens is that your nanonodes are almost always turned off, so they cannot communicate. So the factor their reliability goes to zero, and this is depicted on the graph on the right-hand side, goes to zero for the values that are infeasible in practice. So for the values that are feasible in practice, we should be kind of on the right-hand side on the graph, which is not even depicted, the reliability is zero, which implies that the nanonodes should most of the time be turned off, and then we turn them off when they're needed. So conclusions, there is no simple way to increase reliability. Nanonodes more or less always have to be turned off. And then if we think about in-body applications, it's intuitive that the localization of the nanonodes, which are going to be passively flowing inside of a person's body, so their locations are going to be important. If you think about targeted drug delivery, for example, you need to know where the target is. So we need localization for this set of applications. And the idea in the Scale ITN project is to enable this localization through backscattering. So the idea is that you send the signal which is from an anchor, which is on a person's body, to a nanonode which is inside of a person's body, and the signal is reflected back to the anchor. And if it has multiple anchors, you can then localize the nanonode inside of the body. What is the benefit here? Well, this doesn't consume energy on the level of a nanonode. The nanonodes can essentially be asleep. What is the challenge? Well, the first challenge is combating the terahertz propagation. And the second challenge, which kind of seems to be more interesting in this context, is multiple responses, right? And in the beginning I've shown, I didn't really emphasize on that, but the assumption is that there's going to be a number of nanonodes inside of a person's body. We're talking about thousands to millions of nanonodes. So if you utilize this backscatter-based localization, what's going to happen is an anchor is going to send a signal, and the signal is going to be reflected by multiple nanonodes. And then these reflections are going to be received by multiple anchors. So we have to distinguish between different signals, and we have to kind of find the proper response among many responses that we have. So what are the ideas that you're going to utilize in Scale ITM to combat this problem? One is the random backup, where the nanonode is essentially at certain points not backscattering. If the nanonode is kind of close to the anchor, then more data can be transmitted. So in essence, parts of the whole address of a nanonode potentially can be transmitted in the backscattered signal so that the anchor knows at least partial identifier of a nanonode that has transmitted the response. And there are some trilateration constraints. So since we're going to use trilateration-based localization, the idea is that you get multiple potential possibilities. So you can remove the ones that are kind of outside of the person's body, because we know that the nanonodes are inside of a person's body. Well, this is the first step. Even if we can enable localization of the nanonodes, the question is how reliable these location estimates are. And since we are talking about, say, targeted drug delivery, they better be reliable. So the next thing that we want to do in this project is try to establish what is the quality of the estimated location estimates. Well, what is the quality of the location estimates we get? And is this quality bound inside of a certain, quality interval? So in order to do that, we're going to utilize the intuition of our previous work, which was to feed a neural network with the mappings of, this is the signal feature that were used for localizing this node, and this is the accuracy of localization. This is the quality of localization that we obtain. And then for the new signal features, we can obtain again, the accuracy of localization, which is something that we want to use for the localization inside of a person's body. And these approaches have been kind of published before. Okay, so now we have, assuming that we have localization, the question is, well, is it possible, given that the localization is required by the applications, is it possible to utilize these location estimates to optimize the communication, because we also require communication, right? If you think about applications, you need to somehow instruct the nano node to start, say, drug delivery, or you have to kind of obtain the reading from a nano node. So in this context, the idea is, and obviously because of the range constraints inside of a person's body, we expect multiple hop communication. So the idea here is that you can, by utilizing the same signals as the ones that were utilized for localization in a certain instance, you can instruct the nanonodes to wake up. You remember at the beginning of the slide, I said nanonodes most of the time have to be asleep because of their energy limitation. So you can instruct them to wake up, and you can instruct only the certain nodes that are in your path, and you know the path based on their location. You can wake those up to extract the reading or to deliver some instruction to a nanonode deep inside of a person's body. And the question, there are multiple questions and challenges here. One is the addressing. So how can you address just some nodes on that path, given that there are many nodes inside of a person's body? How much data can you transmit given the distance between the nodes? And all these things are something that we're going to target in the Scale ITM project. And well, this is the final message that I want to deliver, and it says, well, if you have locations of two nodes based on their locations and some knowledge about the environment in which these nodes are, you can pose an estimated value for your signal to noise ratio. You can kind of postulate the estimated value of your signal to noise ratio between these two nodes, and based on that you can estimate the quality of your link. So this approach has been evaluated and proposed in the context of low-powered wide area networks, but there is intuitively nothing wrong with it being applied in the context of in-body nano-communication. So the idea here is, if you have several potential candidates for your multi-hop communication based on the estimated values of the SNR on a link, you can decide which one to take to create your path. And this is my part of the presentation. I just want to give a few intermediate quick conclusions. So we've talked a bit about intermittency, and this has been done in the context of software-defined metamaterials and metasurfaces, but in essence, it holds for all energy harvesting nanonodes, so it can be extrapolated to other domains, application domains enabled by terahertz operating nanonetworks. This kind of more advanced energy consumption modeling has been proposed in the context of, again, software-defined metamaterials, but again, well, it holds for all types of energy harvesting nanonodes. Nano-localization, in this context, we discussed this for in-body applications. In the next talk, in a few hours, I'm going to talk about localization in software-defined metamaterials. Similar approaches can be used also for wireless robotic materials, only the environment is different in this case compared to in-body applications. Localization quality, we were talking about it in the context of in-body communication, but still it could be useful to have that on the level of software-defined metamaterials or wireless robotic materials. So extrapolation here would be useful, and I believe it's also possible, similar with location-aware communication. So this can be applied to various application domains. Okay, and with this, I'm going to give the floor to Sergi. Thank you for your attention, and bye.
Thank you, Filip. I'm gonna continue the presentation where you left it. I'm basically gonna cover the two other applications that you mentioned at the beginning, software-defined metamaterials and on-chip communication. I'm gonna provide a little bit of context and then talk about the work that we have done in the past few years, and then pose some additional questions of possible future work. I'm gonna start by software-defined metamaterials. For those that don't know, metasurfaces or metamaterials are structures composed of arrays of sub-wavelength elements that enable unprecedented control of electromagnetic waves. And it is this sub-wavelength property that provides this new degrees of freedom of electromagnetic control. In particular, you can control the amount of absorption that a surface will incur into the impinging wave. You can control the direction of the reflecting wave, and you also can control the scattering pattern of the reflecting wave in ways that traditional antenna arrays cannot do. So some people have seen an opportunity in providing intelligence to those metasurfaces, so providing ways of modifying the response of a metasurface in a way that it's intelligent related to the application at hand. And some of the possible applications that have been thought by providing this intelligence are given in 6G communications, and some of them are hybrid precoding design, index modulation, indoor signal focusing, and so on and so forth. Many different applications have been appearing in the last few years. So the key question is, how do you provide that intelligence to a metasurface, right? And this is one of the questions that the BioSource project has been trying to answer. In that project, we proposed the hypersurface. Basically, it's the structure that you see here. There's the metasurface layer with the unit cells, and then embedded at the back of the metasurface, there's an array of controller chips. Each of these chips controls a part of the metasurface. It tunes the response of the unit cells, and there's an embedded communication network among those chips. So there's a nanocommunication network within the metasurface. So that's why this is relevant to NanoCom. So the challenges of these software-defined metamaterials related to communications is the dimension of this metasurfaces for a given application. In our case, we need beam steering. So how many unit cells you need to provide good beam steering. Another challenge is understanding the internal communication needs of those metasurfaces. So how many wires do we need to put across the chips to serve that communication, and to design the intersurface network according to the communication needs. So for the first challenge, the dimension of metasurface is basically used an analytical model to check for beam steering, for instance, how the performance metrics of beam steering scale with the number of unit cells or with the sophistication of the chips. And in that case, you can see in this figure, you can see the directivity of the metasurface and the target deviation, so how much the beam is deviated from the target for different parameters, which relate to the amount of unit cells and the sophistication of the chips. So that provided kind of a view of, okay, so if we need a given directivity, which is the minimum amount of chips that we need to put, right? So that provides a proxy for how much communication we will have to provide. So our second question that we try to answer is, how are the communication needs of those metasurfaces? To that end, we assumed beam steering, and we assumed a given movement, right? So we assumed that the person was moving across a room, and that our metasurface was steering the beam towards that user. So that movement and that change of angle of the beam steering device internally incurred into changes of metasurface state, which in the end meant that there was some communication within the chips, between the chips of the metasurface. So that means that this is communication that the chips need to serve. And in that analysis, for instance, we took this person moving across the room, and for the different angles of steering, we saw that depending on the angle, we would have to serve a request of reconfiguration more often. And the range was from 0.1 to 1 second, more or less. So you needed to reconfigure the metasurface on a granularity of hundreds of microseconds, or even tens of microseconds at most, right? We also checked which is the amount of unit cells that needed to change the state as a function of the angle of steering, and that changed over the angle. In the end, we saw that if we aggregated both effects, we could have which is the injection rate of packets of information packets that need to be served within the metasurface, and that took us up to thousands of packets per second. So kilobits per second, even megabits per second of information within the metasurface. So the internal network of the metasurface had to serve up to megabits per second of throughput. So we have an internal network for the metasurface that had to reconfigure in more or less a latency of hundreds of milliseconds and giving a throughput of up to a few megabits per second. So that seems to not be a very stringent or very demanding communication network, but we have to understand that the resources are limited. And if our metasurface has to serve millimeter wave waves, we would have more or less one chip per each wavelength of metasurface. So this, and knowing that the input-output pins for communication between the chips are very expensive, we will have that the topology of the internal metasurface network is going to be very limited. This impacts on the routing possibilities or the fault tolerance of this internal network, and the bandwidth is very low. So these are things that we need to take into account when designing the network that we will have within the metasurface. So with this context analysis in terms of the applications, the amount of communication that we need to serve, and these internal constraints that we have, the outstanding question that we want to solve in the future is how much will these metasurfaces consume and cost, and how much of this consumption and cost will come from the communications. Can we use energy harvesting to power them and to power the internal communication network? Given the input-output constraints of the chips, do we want to have wireless communication within the metasurface so that we don't need to have pins that to physically connect the different chips? Which technologies will allow us to have these wireless communications? So these are the kind of questions that we ask ourselves. So now I'm trying to do more or less the same analysis. I know I'm going a bit fast, but this is the time that I have. I'm going to try to do the same with on-chip communications, right? The content of on-chip communications is similar in the sense that we have a system which is very small and which have different, let's say, different chips within a given system. In this case, the system is a multi-core processor in which the different chips or the different processors make computation in parallel and share data and synchronize by a network on chip. This network on chip is very important because if a packet is delayed, the whole computation is delayed. So this network on chip is essential to have fast computation, right? And it's also very important because it can be responsible to up to half of the power consumption of a computer, of a processor, let's say. So this network on chip is essential. So any improvements that you can do to this network on chip is going to be very important. To put even more context to this is that nowadays, to have higher computational speed, what we do is to put more cores into the processor. And that in turn implies a higher and more heterogeneous network on chip load. And nowadays, network on chips, they react to that with worse network on chip performance. So they have worse delays and worse throughput. So in the end, what that implies is that we will not have the higher computation speed that we were promising by having more cores. So in the end, we will have a slower, less efficient, and less programmable processors. So what we want is the opposite. What we want is to have, better processors. So we want the network on chip to be able to cope with these higher and more heterogeneous workloads. So the response to that challenge is, why don't we use wireless communications? So we take the opportunity that transceivers operating at sub-terahertz and terahertz bands with tens of gigabits per second speeds and quite a good efficiency have appeared, and that we have plenty of space. So they are small enough to be integrated, several of them within a chip. So why don't we try to use them to fix the problems that we have in network on chip? Why don't we try to use them to have a low latency, inherently broadcast and flexible on-chip network, which is something that is missing right now. So why not, right? So what we try to do in this Whiplash project is first to characterize how is the wireless channel within the chip, so how waves propagate within a chip package, and understanding the potential gains of having this wireless network on chip. So if we really can speed up the execution of a computer by using a wireless network on chip. For the first one, on the channel characterization, we started by modeling in a full wave simulator, modeling a computer chip package with the different layers. and modeling on-chip antennas. And then understanding how is the field distribution, how is the path loss, and how is the delay spread. We did that. The results, I'm not going to go into details of the results, but we did it for different parameters of the chip package, for different dimensions, different materials, different thicknesses of the different layers. And then we realized one thing, that these are controllable parameters. That's parameters that the manufacturer can actually choose. So that means that we can engineer the channel. So we took that opportunity to connect the full wave solver to an optimizer, in which the optimizer would change the dimensions of thicknesses of the different parts of the package to see if we can improve the path loss and we can improve the delay spread. And the response is that yes. So if this optimizer was able to optimize the path loss, to optimize the path delay spread, or to have a balance between the two because they are contradicting. The other thing that we addressed in so far is actually simulating a computer architecture that uses wireless to communicate the cores of a multi-core processor. We took an architecture that would take advantage of wireless. We contacted computer architects to make sure that we did something that was meaningful. And we actually saw that this was possible, that we could speed up the applications by 2x. So we were twice as fast as architectures that did not have wireless. And we reduced the computing energy. Sorry. And we reduced the computing energy by 40%. And let me say that this doesn't seem a lot, but this is a lot in computer architectures in which speedups are 10%, 20%, and energy reductions are 5%. So we saw that wireless was very, 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 very impactful in this area. But the questions now are, which are the protocols that we will design to achieving those expected gains? Are these protocols similar to sensor networks? Are these protocols similar to more general wireless networks? What happens when we reach terahertz frequencies and we have higher bandwidths? What if we can do beaming for on-chip communication? What happens if we can have parallel several communications within the chip? And which are the technologies that will allow us to do that? So with this, I conclude the talk just by concluding several things. Both software-defined mathematics and on-chip networks are two area constrained environments, but that have a high impact if we allow wireless terahertz nano networks to happen. Okay, in both cases, we studied the context and we studied the potential gains. So now is the time for the community to think about the protocols and also think about the hardware that will allow us to have these applications. So the last question I want to make is, which is the technology that will provide this opportunity, that will provide those miniaturized antennas and transceiver? Will that be CMOS? Will that be silicon germanium? Will that be graphene? And we have two talks in the sessions today that will try to provide some light into these questions. So acknowledgements from the different projects and from the European Commission that's funded those projects, and then we will be happy to take Filip and I to take any questions. Thank you.